A fuel tube grounded the F-35? No, wait, you're kidding. A stealth fighter can cost around $100 million. It can hide from radar. It can land vertically. It can fuse sensor data from across a battlefield. And in 2022, some of them were stopped by something that sounds almost too boring to be real. A fuel tube. Not a missile. Not enemy fire. Not a software hack. A tube inside the engine system. And the stranger part is this. The tube may not even have been the real villain. The real problem was vibration, a rare resonance inside one of the most advanced engines ever put in a fighter jet. This is no wait, you're kidding. This story starts on December 15, 2022, at Naval Air Station Joint Reserve Base, Fort Worth in Texas. An F-35B was coming down in a vertical landing test. The B model is the Marine Corps version of the F-35, the one that can do short takeoffs and vertical landings. That capability is absurdly complex. The aircraft has to balance thrust, lift, control surfaces, engine behavior, and pilot inputs, while it is basically hanging over the runway on a column of force. In the video of the mishap, the jet descends, touches down hard, bounces, pitches forward, spins, and the pilot ejects. The aircraft is left damaged on the runway. At first, it looked like a crash story. One expensive jet, one terrifying landing, one lucky pilot. But then the story got bigger. The F-35 Joint Program Office restricted some newer aircraft from flying while investigators worked out what happened. Deliveries of new F-35s were affected. Deliveries of new F-135 engines, the Pratt & Whitney engine that powers the F-35, were paused too. That is when the story became much more interesting. Because early reporting pointed to a tube used to transfer high-pressure fuel inside the engine. One small component in one hidden part of the jet's body had become a program-level problem. This is the part of the story where the internet wants the cleanest possible headline. A cheap part grounded a $100 million fighter jet. That headline is tempting. It feels perfect. But it is also the part we need to be careful with. The verified detail is not a 135 price tag. The verified detail is the F-135 engine and a fuel system issue tied to vibration. So the honest version is better. The F-35 was not stopped because a random cheap tube was bad. It was stopped because a tiny physical interaction inside an advanced system created a failure mode big enough to ground aircraft. The F-135 is not a normal engine. It is a massive afterburning turbofan built for the F-35. In the F-35B, it is part of a system that supports vertical landing, which makes the engine environment even more demanding. The engine is dealing with heat, pressure, fuel flow, vibration, airflow, moving parts, software control, and mechanical loads. Inside that world, a fuel tube is not just plumbing. It is part of a system under pressure, bolted into a machine where every component is vibrating, expanding, cooling, heating, and reacting to the components around it. That is what makes aircraft engineering so unforgiving. On the ground, a fuel tube sounds like something you would find in a repair manual. In flight, it is part of a chain that has to behave correctly while fuel is moving. The engine is breathing, metal is heating, control software is making adjustments, and the aircraft is asking for power in very specific ways. The tube does not get to exist in isolation. It has neighbors. It has brackets. It has fittings. It has pressure pulses. It has vibration coming from the engine around it. And if all of those little conditions line up in the wrong rhythm, the part can experience a world that looks normal from the outside but is violent at the point of contact. That is the part of the story people miss. The failure is not always the part. Sometimes the failure is the environment the part is forced to live in. The later explanation from the program in Pratt & Whitney was not simply, the tube was defective. It was a rare harmonic resonance problem. That sounds technical, but the basic idea is simple. Every object has frequencies where it naturally wants to vibrate. Push it at the wrong rhythm and the vibration can grow. That is resonance. It is why a singer can shatter a glass in a physics demo. It is why a washing machine can shake itself across a room when the load is unbalanced. And in extreme cases, it is why a small repeating force can become more dangerous than a single big hit. Inside an engine, resonance is not dramatic at first. It does not look like an explosion. It looks like a part vibrating slightly more than it should. Then doing it again. And again. Thousands of times. Then millions. Metal does not need to be weak to fail this way. It can be perfectly manufactured and still crack if the system around it keeps feeding energy into the wrong vibration. That is the uncomfortable part of this story. The system can be designed by brilliant people, built by elite manufacturers, inspected by professionals, and still hide a failure mode that only shows itself under a very specific combination of conditions. This is also why the F-35 is such a good example. People usually talk about it like it is one thing, a stealth fighter, but it is really a stack of systems: the airframe, the engine, the sensors, the flight control software, the lift fan on the B model, the fuel system, the maintenance system, the supply chain, the test program, the acceptance process. The public sees the jet. The engineers see a moving web of dependencies. And sometimes the part that matters is not the most expensive part. It is the part sitting at the intersection of everything else. That is also why a grounding order can sound more dramatic than it really is, and still be completely rational. When a rare failure mode shows up in aviation, the first question is not, did it happen to every aircraft? The first question is, which aircraft could be exposed to the same conditions? That is why investigators care about build dates, flight hours, part batches, engine configuration, maintenance history, test conditions, and exactly what the jet was doing when the problem appeared. If the risk seems concentrated in newer aircraft with low-time engines, that narrows the search. If it appears during certain operating conditions, that narrows it again. But until the pattern is understood, the safest move is to restrict the aircraft most likely to share the risk. To the public, that can look like panic. Inside an aircraft program, it is discipline. It is the system saying, stop, we need to understand this before we keep flying. After the Fort Worth mishap, the program moved toward a mitigation. The F-35 Joint Program Office eventually cleared Pratt & Whitney to resume deliveries of F-135 engines after a vibration fix. Reports described hardware and procedural mitigation work, including a broader effort to address the resonance concern across the fleet. The point was not that every F-35 was unsafe. The program said the highest concern was around a limited group of aircraft. But in aviation, limited group is still enough to stop operations when the aircraft is this complex and the consequences are this expensive. That is the real lesson. The F-35 was not humbled by something simple because the engineers were careless. It was humbled because extreme machines create extreme interactions. When you push speed, stealth, vertical landing, software, fuel flow, heat, and vibration into the same package, the boring parts become important. A tube can become a headline. A vibration can become a grounding order. A small resonance can move through an entire program. The easy story is, a tiny part grounded a $100 million jet. The better story is, a $100 million jet was only as strong as the quiet physics inside its smallest systems. And that is why this matters beyond one aircraft. Modern technology does not fail only at the obvious weak points. It fails at the hidden connections, the interfaces, the vibrations, the assumptions, the places where every part works alone, but the system misbehaves together. That idea matters far beyond fighter jets. It is the same reason a data center can go down because of a cooling assumption nobody questioned. It is the same reason a spacecraft can be threatened by a valve, a seal, a sensor, or a line of code that looks harmless until the mission depends on it. It is the same reason a financial system can look stable until one small counterparty, one hidden dependency, or one timing problem reveals the structure underneath. The interesting failures are rarely just big things breaking. They are small things connecting. One small part, one specific condition, one vibration, one assumption that was fine yesterday. Until today, it was not. That is why boring components deserve respect. Because in complex machines, boring does not mean unimportant. Boring often means invisible, and invisible is exactly where the next surprise tends to hide. So yes, an F-35 can evade radar. It can land vertically. It can carry some of the most advanced avionics ever built. But it still has to obey physics. And sometimes physics whispers through a fuel tube. No, wait, you're kidding. Subscribe for more stories like this about space, technology, watches, finance, and the systems hiding in plain sight.